Is the screen visible, guys?
Yes, sir.
Right. So let us focus on a new chapter called as magnetism and matter. Okay. So everything in this chapter deals with bar magnet, guys. Okay. You can divide this chapter into three parts again. One will be dealing with bar magnet. The second one will be dealing with the Earth's magnetism, and third one will deal with magnetic materials. These are the three major areas where questions can be asked from this particular chapter of magnetism and matter. If we talk about bar magnet, some basic properties: whatever is electric dipole, same thing will be your bar magnet. Only difference is there we find electric field, here you will find magnetic field. There we will use there we will use epsilon naught, and here epsilon naught will be replaced by 1 by mu naught. There we will have electric dipole moment, here you are going to have magnetic dipole moment. Okay, so basically a bar shaped object you can consider can behave, a bar shaped object with poles can behave as a bar magnet, and the distance between the ends will be called as geometric length. Poles will not be exactly at the end, they'll slightly be inside. The distance between the poles will be called as magnetic length. Magnetic length will be almost 0.84 times the geometric length, guys. And apart from that, whenever we talk about bar magnet directed from south pole to north pole, we are going to have one particular quantity called as your magnetic dipole moment. Whatever is charge in electrostatics, here you are going to have magnetic pole strength, guys, small m. So south pole, if you can consider, it is similar to negative charge. North pole, if you consider, it is similar to positive charge. So charge will, we talk about magnitude of charge. Here we will talk about the strength of the pole. It is also called as magnetic pole strength, guys. So what we can write magnetic dipole moment as, very important again. It is given as magnetic pole strength into magnetic length. What is it given as? Magnetic pole strength into magnetic length. And magnetic pole strength will be similar to the charge, guys, in electrostatics. So let us try to find out the magnetic field due to a bar magnet. Now we are going to have three axes again, right? First of the axis will be that axis passing through the poles and the center. This axis will be called as axis of the bar magnet or axial line. There will be one more axis which is passing through the center of the bar magnet and perpendicular to the axis. So that will be called as your equatorial line. So our interest will be to calculate what would be magnetic field at axial point, what would be magnetic field at equatorial point. Now, leaving out any point on axial line and leaving out any point on equatorial line, you can consider any other point in the plane that will be called as radial point. And at radial point, we will try to calculate the magnetic field only due to a short dipole, guys. Okay. So if you look at the axial point, what is magnetic field at axial point? If I write it in vector form, guys, magnetic field at axial point, if I consider, it will be given as mu naught by 4 pi 2 m bar into r divided by r square minus l square whole square. Now, what is the meaning of a short dipole or a short bar magnet, guys? For short bar magnet, always remember distance will be greater than the length. So, if we take short bar magnet, what we can tell, R value is much more greater than length. It is also called as ideal magnet, guys. Okay, and always remember at axial point, magnetic field will be in the direction of magnetic dipole moment. Just like in electrostatics, electric field will be in the direction of electric dipole moment. Here in magnetism, magnetic field will be in the direction of magnetic dipole moment. Magnetic dipole moment will always be directed from south pole to north pole. Clear? Is that clear? In the same manner, you take any point on the equatorial axis, that will be called as your equatorial point. And what will I get magnetic field at equatorial point in vector form if I write? Magnetic field at equatorial point will be mu naught by 4 pi minus m bar divided by r square plus l square whole power 3 by 2. There, what do we get, beta? In electrostatics, in place of mu naught, you will get 1 by epsilon naught. In place of m bar, you are going to get p bar. Clear, all of you? Rest all will be same. In place of magnetic field, you will get electric field. So electric field will be 1 by 4 pi epsilon naught 2 p bar into r divided by r square minus l square whole square. Similarly, electric field at equatorial point will be 1 by 4 pi epsilon naught minus p bar divided by r square plus l square whole power 3 by 2. If I take a short bar magnet, right, for short bar magnet, you can write magnetic field at axial point is mu naught by 4 pi 2m by r cube, and at equatorial point it is mu naught by 4 pi m by r cube. To write it in vector form, it will be minus m by r cube, guys. So what we can tell, if you just compare both of these, right? And I'm talking about short bar magnet, guys. So for short bar magnet, magnetic field at axial point will be 2 times the magnetic field at equatorial point. This is only in scalar form, guys. If I write it in vector form, magnetic field at axial point will be minus 2 times the magnetic field at equatorial point. Is that clear? Yes or no? And how can I represent short bar magnet? You can represent it simply by a short line. And arrow mark should indicate the direction of magnetic dipole moment. So leaving out a point on the axial line and a point on the equatorial line, any other point can be considered as a which point, beta? Radial point. And what would be the magnetic field at radial point? It is mu naught by 4 pi m by r cube under root of 1 plus 3 cos square theta. Okay. Now if I assume this to be x-axis, do we have magnetic dipole moment along x-axis, beta? Yes. So if radial angular position is theta, I'm also going to get this angle as theta. So what is angle between? This is your m bar. This is your magnetic field radial point. So what is the angle between? What is the angle between magnetic dipole moment as well as magnetic field radial point? It will be equal to what? Theta plus alpha. Clear, all of you? Now you see, magnetic field axial point is parallel to m bar. We already know that. Equatorial point anti-parallel to m bar. This also we know, right? Here, if you look at the third point, guys, what is this point here? This is magnetic field at radial point again. So at radial point, if magnetic field at the radial point is perpendicular to dipole moment, theta plus alpha value will be 90. Or I can write tan theta value as root 2. I can also write cot theta value, you can write, beta. Cot theta value, you can write it as 1 by root 2. In the same manner, I can write cot alpha will be root 2. And I can write tan alpha will be 1 by root 2. Clear? Right? Due to a short dipole, if I take magnetic field at axial point, mu naught by 4 pi 2 m bar divided by r cube. If I take it equatorial point, mu naught by 4 pi minus m bar divided by r cube. At radial point, mu naught by 4 pi m by r cube under root of 1 plus 3 cos square theta. Clear, everyone? Yes or no? We have magnetic field lines, guys. What do magnetic field lines do? Basic things we are studying again. They are going to represent magnetic field. Electric field lines, if you take, can they form closed loops? Induced electric field lines can form closed loop. However, magnetic field lines will always form closed loops, guys. They're always closed continuous curves. If you want to find direction of magnetic field at any point, what will you do? You will draw tangent drawn will give us direction of magnetic field at that point. So whenever you draw tangent, it will give direction of magnetic field at that particular point, and no two magnetic field lines can intersect, because when they are intersecting, We'll have two directions of magnetic field, which is not possible, guys. Outside the bar magnet, directed from north to south, you can take outside the bar magnet, directed from north to south, and inside a magnet, they'll be directed from south to north. Clear, all of you? These are basic properties of magnetic field lines. They are going to represent magnetic field in a region, right? They're called as, they will always be closed continuous curves, guys. And if you want to find direction of magnetic field at any point, at that point you are simply going to draw a tangent. They cannot intersect, because at the point of intersection you will have two directions of magnetic field, which is not possible. Clear, everyone? Yes or no? Um, as I said you, just like you take electric dipole, you have negative charge and positive charge. In the same manner, for a bar magnet, you will have south pole and north pole. So here poles are similar to charge, right? I've already told you that point, guys. So if you look at this particular case, it is represented by small m. Unit we can write ampere meter. So it is equivalent to charge in electrostatics. Clear? So whenever we are talking about the magnetic pole strength, very simple logic, guys. Positive charge, where will it experience force? If positive charge is placed in an external field, it will experience force in the direction of electric field. Yes or no? And when negative charge is placed in the external electric field, it will experience a force opposite direction of electric field or not? In the same manner, whenever a pole is placed in a magnetic field, external magnetic field, right, it will experience a force M into B bar. A north pole will experience force in the direction of applied magnetic field. South pole will experience a force opposite to the direction of applied magnetic field. Just like when a charge is placed in a external electric field, it experiences force. In the same manner, you can consider a pole placed in an external magnetic field will also experience a force, whose force will be given as M into B bar. Is that clear? Yes or no? So you can also say it is the number, uh, magnetic pole strength we are talking about, no? So what do we write? Basically, magnet dipole moment. Magnet dipole moment, if you study in moving charges, we have seen that it is N into I bar. Here, what did I get? I got it as M into 2L bar. So are they both similar? Left hand sides are similar or not? What we can write? I into A bar can be equal to M into 2L bar, guys. So what is pole strength here? It is I into A bar divided by 2L bar, right? So directly remember, pole strength will always be proportional to area of cross section. Clear, all of you? Is that clear, everyone? Whenever a pole is placed in an external magnetic field, it will experience a force. North pole will experience a force in the direction of magnetic field. South pole will experience a force opposite to the direction of magnetic field. So I can write the pole strength as I into A bar divided by 2L bar. Clear, all of you? What is magnetic flux if I consider? What is magnetic flux, guys? Basically, magnetic flux is given as B bar dot A bar for which type of field? For uniform field, guys. Or I can write it as BA cos theta. In the same manner, right? If you have variable field, then you write it as integral B bar dot dA bar or integral B bar dot ds bar. So what is magnetic field? Magnetic flux? It is the number of magnetic field lines passing per unit area and normal to it, guys. That will be called as magnetic flux. If we have uniform magnetic field, flux will be given as dot product of magnetic field and area vector, which is BA cos theta. And if you have non-uniform varying field, then flux will be given as integral B bar dot dA bar or B bar dot ds bar. Clear? Yes or no? What is Gauss law stating? Very simple logic. Gauss law is stating that you apply wherever you want to apply magnetic flux and all, but if you try to calculate the magnetic flux with a closed surface, and where it should be placed, it should be placed in a uniform magnetic field. Clear? So whenever a closed surface is placed in a uniform magnetic field, the flux associated with that surface will be zero. Clear, all of you? So, what we can understand from that? We can understand that magnetic monopoles do not exist, guys. Clear, everyone? So, only north cannot exist, only south cannot exist. If north is there, definitely it will be accompanied by south. If south is there, it will definitely be accompanied by north. Clear? Just give me a minute, I'll apply something and come. It's raining a lot. Am I audible? Hello, visible, audible?
Yes, sir.
Hmm. Right. So we are talking about bar magnet, guys. We have some point called as geometric length. Any rectangular shaped object with poles will be bar magnet. We have something called as the geometric length, which is the distance between the edges. And when we talk about the poles, they're not going to lie exactly at the edges. They'll be slightly be present inside the edges. So distance between the poles will be called as magnetic length. So just like electric dipole, south pole will behave as a negative charge, north pole will behave as a positive charge, and the magnetic length will be 0.84 times the geometric length. So magnetic dipole moment, just like we have electric dipole moment, right, where a quantity will be directed from negative charge to positive charge. In the same manner, in case of bar magnet, there will be a physical quantity directed from south pole to north pole called as magnetic dipole moment. It will be given as magnetic pole strength times of magnetic length, guys. Then we tried to find out magnetic field due to a bar magnet. At axial point we have seen what is it, and at equatorial point we have seen what is it. For short bar magnet, what will be magnetic field at axial point? What will be magnetic field at equatorial point? What is the relation between magnetic field at axial point and equatorial point for short bar magnet? How to calculate the magnetic field at radial point? At radial point, we can calculate only due to a short magnet or ideal magnet, guys. Clear? Theta will be the angular position. So at radial point, if magnetic field at radial point is making usually magnetic field at radial point makes an angle theta plus alpha at magnetic theta plus alpha with magnetic dipole moment, right? So if magnetic field at radial point is perpendicular to magnetic dipole moment, theta plus alpha value will be 90 degrees. Then we can write theta value will be tan inverse of root 2 and alpha value will be cot inverse of root 2. Clear all of you? Then we talked about properties of magnetic field lines. Usually, what do? They represent magnetic field in a region. They're always closed continuous curves. You want to find direction of magnetic field, you'll simply draw a tangent at that particular point. They cannot intersect because at the point of intersection, it will have two directions, which is not possible. Outside directed from north to south, inside it will be directed from south to north. Clear? Then we are talking about magnetic pole strength, guys. See, magnetic pole strength is similar to charge in electrostatics. So whenever a charge is placed in external electric field, will it experience force? Yes. In the same manner, whenever a pole is placed in external magnetic field, it will also experience force. North pole will experience force in the direction of magnetic field. South pole will experience force opposite to the direction of magnetic field. Right? We also talk about how pole strength is proportional. Pole strength will depend on area of cross section. More is the area of cross section, more will be the strength. Lesser the area of cross section, lesser will be the strength, guys. Clear all of you? So I can write pole strength as I into A bar divided by 2L. Current is given, area is given, length between the poles is given. Then directly, blindly, you can apply this formula. Clear all of you? In the same manner, we are talking about magnetic flux. So what is magnetic flux? Just like electric field. Electric flux represents the number of electric field lines passing per unit area and normal to the surface. In the same manner, magnetic flux is also number of magnetic field lines crossing a unit area, guys, and normal to the surface. If you have uniform magnetic field, then I can write magnetic flux as b bar dot a bar, which is ba cos theta. If you have non-uniform field, then I am going to make use of integration. And what did Gauss say, guys? Whenever you are taking a closed surface, placing it in a uniform electric field, right? The uniform magnetic field, the flux associated with that surface will always be zero. Clear? Clear, all of you? And let us talk about torque on a bar magnet, or to be precise, it is simply the bar magnet placed in a uniform magnetic field. So, few points we need to remember again. Whenever bar magnet is placed in a uniform magnetic field, whatever may be the position, net force is zero. Torque will always be given as m bar cross b bar. Maximum torque will be mb, minimum torque will be 0, and in general I can write torque as mb sine theta, where theta is the angle between m bar and b bar. Clear? Which we have also found out. And what will be the expression for potential energy, beta? Potential energy stored in a bar magnet will be minus of m bar dot b bar, right? Now, because net force on the dipole is 0, net force is 0 means, is it in translation equilibrium or not? Yes. How many types of translation equilibrium we have? How many types, beta? We have three types of translation equilibrium. What are those? First one happens to be stable equilibrium. So here you are going to have stable equilibrium. Then you will have unstable equilibrium. And then you will have neutral equilibrium. So for stable equilibrium, what are the conditions? For stable equilibrium, if I take. For unstable equilibrium, let us take. For normal equilibrium, neutral equilibrium, let us take. So for stable equilibrium, theta value will be 0 degrees. Okay. So what will be the torque, beta? Torque will be 0 again in this case. What will be potential energy? Is it minus mb cos theta or not? So directly you can write potential energy will be minus mb, which is the minimum value, guys. So this energy is which value? Minimum value of potential energy. Force, so anyhow, it is going to be 0 itself. Unstable equilibrium, the angle between the magnetic field and area vector is 180 degrees. So torque will again be 0. Potential energy will now become plus mb beta, which is maximum. And what is the force again? Anyhow, it is 0. Neutral equilibrium, theta value will be 90 degrees. Torque value will be maximum, guys, in neutral equilibrium. The torque value will be m into b. Right? This will be the maximum value of torque. Which value? Is the maximum value of torque, guys. What is potential energy? Cos 90 is 0 or not? So here you can take potential energy 0. Force will always be 0. Clear, all of you? So whenever a bar magnet is placed in a uniform magnetic field, some 5 to 6 points you need to remember, guys. What are those? First is torque experienced. Torque will be given as m bar cross b bar. In general, you can write mb sine theta. Force experienced on it will always be 0. Torque may be 0, may not be 0. Yes or no? Right? So what is the force experienced? Always 0. Torque is m bar cross b bar. Right? And potential energy stored in the bar magnet will be minus m bar dot b bar. Right? So they'll ask you what is the work done in rotating the bar magnet from some angular position theta 1 to angular position theta 2. Again, it is also very important formula beta. It is mb cos theta 1 minus cos theta 2. So bar magnet in uniform field, it will never experience force. It may or may not experience torque. Whereas if it is placed in a non-uniform field, it will always experience force. It may or may not experience torque again. So if you look at this, the bar magnet in a non-uniform magnetic field, it seems, it experiences a net force, may experience a torque, may or may not experience a torque. Clear, all of you? These 5 6 points you need to remember again. Bar magnet in a uniform magnetic field, guys. Clear? Is that fine, all of you? So in all the cases, net force will be how much? 0. So when net force is 0 means it will be in translation equilibrium. How many types of translation equilibrium? 3 types: stable, unstable, neutral. Stable equilibrium, what will I get? Potential energy should be minimum. Unstable equilibrium, potential energy should be maximum. Neutral equilibrium, potential energy should be constant or 0. Clear? Then let us talk about oscillations of a bar magnet. Rest all will be same, guys. Whatever we do for dipole, same things we'll study here. Bar magnet is kept in a non-uniform magnetic field, produces a so what they're asking, oscillations of a bar magnet in magnetic field they're asking. Right. So what we are doing is first we will place the bar magnet in stable equilibrium position. As soon as I slightly displace, there will be a restoring torque acting on the bar magnet and it will perform oscillations, guys. Time period will be given as 2 pi root over I by mb. Angular frequency will be root over mb by I. Clear? Whenever a bar magnet which is placed in a uniform magnetic field is slightly disturbed from its stable equilibrium position and released, then it is going to execute simple harmonic motion with a time period 2 pi root over I by mb. There it will execute 2 pi root over I by pe. They will be writing, guys, in electric dipole again. Clear, all of you?
Yes.
In the same manner, right? We talk about cutting of the bar magnet. Two very important things you need to know. There are two ways in which bar magnet can be cut. Suppose if I take the bar magnet, I can either cut it vertically using a vertical cross section, or I can cut it horizontally, guys. So always remember, whenever you are cutting it vertically, right, what will happen? Magnetic position is changing? No. Area is changing. So obviously the magnet dipole moment will also change. But please understand, Whenever you are cutting the bar magnet perpendicularly into equal halves, guys, the time period will become equal to t divided by n. Time period will get reduced, guys. Clear, all of you? Whereas in this case, right, how did you cut it? You have cut it, sliced it horizontally, guys. So please remember, whenever a bar magnet is cut horizontally, right, in that case, suppose if I say you are cutting it into two pieces, time period became t by 2. If you are cutting into n pieces, time period will become t by n. However, when we slice the bar magnet horizontally, you can slice in n number of ways, guys, horizontally. Time period of each part will still remain same, which is the time period of the original bar magnet. Understood? Yes or no?
Yes.
Right. Then we have two bar. This is also the working of vibration magnetometer, guys. So now you are going to place two bar magnets such that their like poles are tied together. In second case, we are placing two bar magnets in which unlike poles are tied together. So in first case, both the moment of inertias and momentums are lying together. What is time period? 2 pi root over I1 plus I2 divided by M1 plus M2 into V. Second case, if the polarities is reversed, then I will get time period as 2 pi root over L1 plus L2 divided by M1 difference M2 into V. Here both moment of inertia is scalar quantity again. Both the masses are in same direction. Here also moment of inertia stable. But how are they connected, guys? In such a way that, so as you can see, this is south, this will be north, this is south, this is north. So are they placed in such a way that the unlike poles are connected together or not? Yes. So in which case is time period more? T2 or T1? T2 is more or T1 is more, beta?
So T2.
Obviously T2 will be greater, right? He'll ask you to find the ratio. Suppose T1 and T2 are given. Then in that case, what we can write, beta? Time periods are given, let us say. So what we can write? Okay, let us not go in detail about that. So whenever two bar magnets are connected in such a way that their like poles are connected, magnet dipole moment will be sum of individual dipole moments. Unlike poles are connected, magnet dipole moment will be difference of the individual magnet dipole moments, guys. Clear, all of you? Which time period will be greater? Second case, where unlike poles are connected together, time period will be greater. So let us say if time periods are given, then if time periods are given, they will ask you to find the ratio of magnet dipole moments, guys. So basically it is given as T2 square plus T1 square divided by T2 square minus T1 square. What I'll do, I'll take T2 common, guys. So if I take T2 common, what will I get? M1 by M2, you will get it as 1 plus T1 by T2 whole square divided by 1 minus T1 by T2 whole square. Is that clear? It's a very important case again. When you know the time periods for these two alignments, when you know the time periods for these two alignments, can we calculate the ratio of their magnet dipole moments? Definitely we can calculate. So what is the ratio of the magnet dipole moments? You'll get it as 1 plus T1 by T2 whole square divided by 1 minus T1 by T2 whole square. Clear, all of you? Yes or no?
Yes, sir.
So I'm feeling a lot of pain in the throat, guys, and I don't believe I don't think that I can take for a long time. However, we'll try to complete the review of magnetism and matter. So that is first part of your magnetism and matter, which deals with bar magnet, guys. Let us see Earth's magnetic field. So we'll take two plane surfaces. In one plane surface, you will have geographic north, south, east, west. In other plane surface, you have magnetic north, south, east, west. Okay. So what we can consider, that particular plane surface which contains geographic north, south, east and west will be called as your magnetic meridian. Sorry, geographic meridian. And that particular plane which contains the magnetic north, magnetic south, magnetic east, magnetic west. Those are called as magnetic meridians, guys. And always remember, geographic meridian and magnetic meridian will be inclined to each other at a particular angle. What is that angle called as? Angle of declination, right? The angle between geographic meridian and magnetic meridian will be called as angle of declination, guys. And whenever you take a vertical compass and place it in magnetic meridian, the needle of the vertical compass will point towards B bar. So angle made by the B bar with the horizontal of magnetic meridian, it is called as angle of dip, guys. Clear, all of you? So if you can resolve the Earth's magnetic field, you will have three components now. BH will be given as B cos phi. BV will be given as B sin phi. I can write BH square plus B V square to be as B square, guys. And we also have tan phi value will be given as vertical component divided by horizontal component. Now, very important point that you need to know, right? Whether you take magnetic meridian or you take geographic meridian, right? What will be same? Vertical components will be same. Whether you take geographic meridian or magnetic meridian, vertical component will be same. That is the reason vertical component of Earth's magnetic field will not be the source, guys. Again, clear, all of you? Vertical component of magnetic field will not be considered as the element of Earth's magnetic field. What will be considered as the elements of the Earth's magnetic field, beta? Three things again: horizontal component of the Earth's magnetic field, then angle of declination and angle of dip, guys. These three will be called as elements of Earth's magnetic field. Vertical component will not be called as the element of Earth's magnetic field. Why is it not called as element of Earth's magnetic field? Because it is providing it to all the planar objects, guys. Clear? Is that clear?
Yes.
So what is the resultant magnetic field that I'm going to get? Resultant magnetic field, if I want to write, it will be under root of horizontal component square plus vertical component square, right? And if I want to find the value of phi, it will be given as tan inverse of, what we can write, beta? You can write it as tan inverse of BV divided by BH. Is that clear? Now, so we took geographic meridian, we took magnetic meridian, and we got to know that both of them will always be inclined to each other, called as angle of declination. Yes or no? Right? And whenever you take needle of the vertical, we take a vertical compass and place it in magnetic meridian, it will always point towards this needle. What I've done, I've just resolved this magnetic field into two components, horizontal and vertical. Vertical component of Earth's magnetic field will be same for magnetic meridian as well as geographic meridian. That is the reason vertical component is not called as element of Earth's magnetic field. What are the elements of Earth's magnetic field, beta? Angle of declination, angle of dip, right? And what is the other thing? Horizontal component of Earth's magnetic field. Clear, everyone? Yes or no? Now, let us take, suppose, what is dip circle? It is again a device which is used to measure the magnetic field. So, if the dip circle is lying in magnetic meridian, the angle of dip will be called as true dip. But if the dip circle is lying in any other uh, meridian, guys, or in any other plane other than magnetic meridian, then angle of dip will be called as apparent dip, guys. Clear, all of you? So whenever dip circle is lying in the magnetic meridian, this meridian, then it will be called as true dip. But if it is lying in some other meridian, guys, then it will be called as apparent dip, guys. Angle of dip will be called as apparent dip. Now there are some points that you need to know. Some basic statements, guys. We have agonic lines, right? We have isogonic lines. We have aclinic lines. We have isoclinic lines, and we also have isodynamic lines. Can you please tell what are agonic lines? A usually stands for zero, guys. They are the lines joining points of zero angle of declination, right? What are isogonic? Iso means same. They're going to join the points of equal angle of declination. Aclinic, it is continuous locus of points which are going to join, right? So aclinic line, you can consider zero angle of dip, guys. All those points which, or you can say all those lines which join points of zero angle of dip will be called as aclinic, and all those points which join equal angle of dip points, guys, then they are going to be called as isoclinic. Similarly, isodynamic lines are those lines which have same horizontal component of Earth's magnetic field. Beta. Clear, all of you? So usually, dip circle will lie in magnetic meridian. Suppose I am saying if it is lying in some other medium or in another meridian or in another plane surface, then angle of dip will be called as the apparent dip, guys. Okay. So what is the relation between true dip and apparent dip? We can write cot square phi plus should be equal to cot square phi 1 plus cot square phi 2. Is that clear, all of you? Yes or no?
So what is the difference between magnetic meridian and geographic meridian?
देखो भाई, compass will point towards some meridian. You may be, suppose if I say geographic north, it is exactly towards your north, towards forward direction. Geographic south, backward. Geographic east to the right, and geographic west to the left. They are all going to lie in a horizontal plane. So that plane in which geographic north, south, east, and west will lie, this plane will be called as your geographic meridian. What is magnetic meridian? Right? That particular plane in which what is going to lie? Magnetic north, south, east, west. What is the meaning of magnetic north, south, east, west? Suppose if I am keeping a compass right in front of me, I know according to me north is forward. If I take a compass and place it in front of me, that compass is showing north like this. So is there some deviation or not? Or like this? Is there some deviation?
Yes.
So that deviation is only called as angle of declination. So there will be lines which join zero angle of declination. There will be lines which join equal angle of declination. There will be lines which join points of zero angle of dip or points of equal angle of dip. So based on what is the value of angle of declination and categorize them as agonic, isogonic, aclinic, isoclinic, and isodynamic. Is that clear?
Yes. Simply.
So dip circle is usually an instrument which measures the magnetic field. If it is lying in magnetic meridian, angle of dip will be your true dip. Okay. But if it is lying in some other plane, it is not geographic meridian also, it is lying in some other plane, then in that case, angle of dip will be given as apparent dip, guys. Clear, all of you? There is one relation between real true dips as well as apparent dip. Cot square phi will be cot square phi 1 plus cot square phi 2. Is that clear? Yes or no?
Yes.
Right. So let us talk about, so this is the that was the second part of magnetism and matter, guys. First part deals with bar magnet direct formulas, you remember. Second part will deal with earth's magnetism, whatever points we have discussed. Third points will deal with magnetic materials. So we can categorize any material into three types, guys. Either dia, para, or ferro will all depend on some magnetic. What are those magnetic properties? If I say we have around five magnetic properties. The first property happens to be magnetic intensity. It is also called as magnetizing force. It will be given as the ratio of applied magnetic field to the absolute permeability. Then we have intensity of magnetization. What is intensity of magnetization? It is magnetic moment developed per unit volume. I can also write it as pole strength per unit area. Magnetic moment developed per unit volume, or I can also write it as pole strength per unit area. Then we have something called as magnetic induction, right? Or it is also called magnetic flux density. It is similar to flux, guys, again. And how will it be given? Applied magnetic field plus mu naught into I. Okay. Now, based on these three magnetic properties, we have two quantities called as, the first one will be susceptibility and the other one will be relative permeability. Is that clear? So susceptibility is the ratio of intensity of magnetization to H value, magnetic intensity. What is relative permeability now, or magnetic permeability? If I say, it will be the ratio of the magnetic flux density to H. How can I write B value? Just now you have seen B value can be written as mu naught into H plus I. So what we can take, beta? Mu naught into H plus I divided by H. So I'll get mu value as mu naught into 1 plus I by H. So what is mu by mu naught? Mu by mu naught is called as relative permeability, which is given as 1 plus I by H. Clear? The relative permeability will be reciprocal of mu by mu naught, which can be written as 1 plus chi m. Clear? Yes or no? Five properties: magnetic intensity, intensity of magnetization, magnetic flux density, then we have susceptibility and permeability. Okay, that clear?
Yes.
Based on these five properties, we can categorize the materials into para, dia, as well as ferro. Ferro and paramagnetic will have similar properties, so we'll study them separately. Let us talk about diamagnetic, guys. You need to remember all these values again. For diamagnetic, susceptibility is small and negative. Because it is small and negative, relative permeability will be less than 1. So these are some properties again. How will they get magnetized? They get magnetized weakly, opposite to the applied magnetic field. Okay. And magnetic lines do not cross through them. Similarly, when freely suspended, it gets aligned perpendicularly, guys. In the same manner, are repelled by magnetic field. Is that clear? These 5 6 points you need to remember. Susceptibility small, negative, mu r value less than 1, magnetic lines of forces do not cross through them, and whenever you are suspending the wire magnet freely, it will point towards north south direction, and they'll always be repelled by the magnetic fields. Clear, everyone? Or no?
Yes.
Same manner, paramagnetic and ferromagnetic will have similar properties. So basically, they are going to get magnetized strongly, get magnetized in the direction of applied field. Okay, right. So they are going to get magnetized strongly. If I take ferromagnetic, they are going to get magnetized more strongly. So for paramagnetic, you remember, chi m value is small and positive. But for ferromagnetic, you see, chi m value is large and positive. Susceptibility is large and positive. Magnetic field lines can cross through them. When freely suspended, it will be along the axis between North Pole and South Pole. And these will be attracted by the magnetic field. Clear? Yes or no, everyone? Did you understand? Please remember the values. For paramagnetic, chi m is positive small, mu r is just greater than 1. For ferromagnetic, chi m value will be more. So Z value will also be more. Clear, all of you? Z, it seems. Chi value will also be more. Is that clear, everyone?
Yes.
So please remember, susceptibility for diamagnetic small negative, for paramagnetic small positive, for ferromagnetic large positive. So relative permeability for diamagnetic less than 1, for paramagnetic greater than 1, whereas for you can consider ferromagnetic, it will be much more greater than 1. Magnetic field lines can cross through them. When freely suspended, it will get aligned along the direction of applied magnetic field, and what we can consider, they are going to get attracted towards the magnetic field. Clear, all of you? Let us see the susceptibility variation. So for paramagnetic materials, how will susceptibility vary? For paramagnetic, it is inversely proportional to temperature. So because it is inversely proportional, can I take, it will follow rectangular hyperbola beta? Yes or no? Is that clear?
Yes,
That
sir.
is Curie law. Whereas if we talk about the susceptibility with temperature for dia, guys. First one is anyhow para. Susceptibility with respect to temperature for dia. What is it going to be? Is it depending on temperature? No, it is independent of temperature and its value is negative. So you are going to get a graph something like this. Clear all of you? For paramagnetic, the susceptibility is inversely proportional to temperature. For diamagnetic, it is independent of temperature. Okay, and we have one more law called as Curie-Weiss law. What is Curie-Weiss law stating? What is Curie-Weiss law stating? It is stating that as temperature increases, the susceptibility of ferromagnetic materials will decrease. And above a certain temperature, ferromagnetic will get converted into paramagnetic. Clear all of you? So if I plot, very important case again, if I plot the variation, right, for susceptibility versus temperature for ferro. So what is Curie law stating? What is it stating, beta? Decreases with increase in temperature. It will follow some graph in this manner. Then, right, after a certain temperature called as Curie point, right, above this temperature, it will become paramagnetic. So when it is becoming paramagnetic, you can take rectangular hyperbola. Clear all of you? So these are the variations of susceptibility and temperature for para, dia as well as ferro. Clear everyone? As you can see, the variation of I versus H for diamagnetic. Basically, what is susceptibility for diamagnetic? We know it is given as I bar by H bar. Is it negative or not? So what will I get I bar value as? Minus K into H bar. So where is I bar represented? On Y axis. Where is H bar represented? On X axis. Is the following Y is equal to mx graph? But what is the slope? Negative slope, guys. And small slope. So that is the reason you'll get very small value. For paramagnetic, instead of writing minus K, you'll write plus K. So as you can see, slope is positive but small, guys, for paramagnetic. For dia, slope will be negative and small. However, when you look at ferromagnetic, guys, if you increase the applied magnetic field, H bar is nothing but applied magnetic field. If you keep on increasing the applied magnetic field, right, intensity of magnetization will also increase. Clear? Now below this temperature, sorry, below this value of magnetic field, right? See, let us say from here to here, applied magnetic field increasing. No, from here to here, H is increasing means applied magnetic field will increase. As soon as you are switching it off, it is observed that it is not going to come down following the same graph, but there is a small deviation observed. So we will majorly focus on 2 points. This is one point, this is one point. Let us talk about OB point, guys. Right? At point B, or where is this point B? Is it on Y axis? So what is the value of X axis here? 0. So what will this value be? Right? It is the residual magnetism left in a material when applied magnetic field is turned off. So this will be called as your residual magnetism. Is that clear? Now, if I want to remove this residual magnetism, I am going to apply a reverse electric field, reverse magnetic field, guys. So this particular magnetic field will be called as coercivity, guys. This is called as your residual magnetism, or basically it is called as retentivity. So whichever has more retentivity and more coercivity, those will be utilized for making permanent magnets or hard magnets. Those who have lesser value of retentivity and lesser value of coercivity, right? Those are going to be for soft iron, or you can say for temporary magnets or soft bar magnets, guys. Clear, everyone? Yes or no?
So what is coercivity?
Coercivity is, देखो, you take any material, you take basic, you take stainless steel, and you're applying some external magnetic field. Will that stainless steel also get magnetized? Will it also behave as magnet or not?
Yes.
Yes. So whenever you are applying some field, it is getting magnetized. Even if you remove field, there will be some magnetism left in the whatever material you are taking. So that residual magnetism is called as retentivity. So if I want to remove the residual magnetism, I'll apply some reverse magnetic field. So what is the reverse magnetic field here?
Coercivity.
Coercivity. Clear?
Yes, sir.
Any doubts in whatever we have discussed, guys? These graphs are important. Curie law, please remember, the susceptibility inversely proportional to absolute temperature. For diamagnetic material susceptibility, no change at all with temperature. Right? For ferromagnetic materials, what happens to susceptibility? It decreases with increase in temperature. At a certain temperature called Curie point, what is going to happen? The ferromagnetic will get converted into paramagnetic. These are the properties of para and ferro, guys. Similarly, we have also discussed the properties of diamagnetic materials. We have seen different properties, and we have seen Earth's magnetism, right? What is the relation between apparent dips as well as true dips? What are the elements of Earth's magnetic field, right? And basic cases of bar magnet we have discussed. Is that clear, all of you? Yes or no?
Yes, sir.
So unfortunately, I have to stop the session, guys, because right, you'll believe or not, from morning I was not able to talk as well, right? So I just had a skew and all just to make it free motion of sound waves again. So I have to stop now, guys. Any doubts in the review of magnetism and matter? Whenever you are slicing the bar magnet horizontally, time period of each part will remain same. When you are slicing it vertically, time period will get reduced by 2 times or n times. Okay, is that clear? Is that clear, all of you?
Yes.
Yes,
Yes,
sir.
sir.
We'll do the questions of magnetism and matter tomorrow, and you'll also have a test tomorrow on moving charges and magnetic effects of current as well as magnetism, guys. Is that clear?
Yes, sir.
So apologies for today. We'll meet tomorrow. Till then, take care, everyone. Thank you all.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, guys.